Hi, my name is José Benavides. My collaborators are Mario Valli and Laura Sales, and I talk to you about Splashback Ultra-Diffuse Galaxies. So in the scalar relation for galaxies, we have different combinations, normally between velocities, sizes, masses, surface brightness, luminosities, and others. In this plot, we have a relation between sizes and magnitudes. At the left, we have the normal or massive galaxies, and the right, we have the dwarf or less massive galaxies. For massive galaxies, this relation is well defined, but for a dwarf galaxies, this relation presents large scatter. So we have, for the same magnitude or stellar mass, what we call normal dwarf galaxies, but we also have both extended and compact galaxies. From those extended, a class that has gained popularity these last years are the ultra-diffuse galaxies, or UDGs. These are a kind of dwarf with extreme low surface brightness. Here in the right, we have one example of UDGs in coma cluster from the work of Van Dokken. Typically or traditionally, these UDGs live in clusters or groups, or in general, high-density environments. But it's important to study these populations of UDGs in all environments, from high density until low density, with their respective properties. This work of Pro about quiescent LSBs and UDGs using data of gamma spectroscopic survey generate in us a great motivation, because the star-forming galaxies of all kinds is very normal, but quiescent galaxies, and in this case LSBs and UDGs in low-density environments, are very strange and generate in us questions like how did they quench? And in the simulations, we could detect these UDGs. So we use data of a TNG50 simulation, and there we're looking for these UDGs that live in low-density environments. These simulations has a great resolution for particles, so we can resolve and analyze dwarf galaxies with a great resolution. For this, we define as UDGs those galaxies with stellar masses between 7.5 to 9 in log scale and above of 95% of mass size distribution, or 55% of high size tail in this distribution. We found a several number of central UDGs located in low-density environments, highlighted with magenta stars in this plot. Also, we include some observational data for UDGs in the coma and Brio cluster, and also UDGs in low-density environments. Our definition of UDGs overlaps very well with observational samples. In this plot, we have the relation between color and stellar mass. And all dwarf is indicated with a gray dots in the background. And we include the star symbols for our sample of UDGs. We find that low-density UDGs are typically blue, but to our surprise, we found a population that occupies the red sequence. We refer to them as blue and red UDGs in what follows. And their colors are very well correlated with the star formation rate. where the red UDGs appear like quenched galaxies, and the blue UDGs are located in the main sequence of the distribution. These two populations of UDGs separate in other properties as well corresponding. For example, in the left panel, we have differences in the ages of the stellar populations, where the star-forming galaxies are very young, in contrast with the old population of quenched UDGs. Here, yellow diamond represents the average of a subsample of UDGs in common, and the blue diamond corresponds to an average of UDGs in the field. In the central panel, we have the kappa rod parameter, which is an indicator of morphology. Above of 0.5, we have a disk structure, and below, preferentially, spherical morphologies. So our red UDGs are all dominated for sphericals, and some part of our blues UDGs have a disk structures. And in the right panel, we have a relation between stellar mass and heavy mass. We can see that those quenched galaxies are dark matter deficient compared to the blue population. All of this compared with the abundance matching relation by Monster. And other question is where they distribute this population of red UDGs. So looking for the formation histories of quenched UDGs, we realized that they were all splashback objects, meaning that although they are today centrals in the fields, but in the past they had been satellites of more massive halo. Here in the top panel, we show the distance to the host versus time for one of our quenched UDGs. This splashback orbit means that it was inside the virial radius around of 9 megayears, but due to the large apocenter, the orbit is today about of 1.5 megaparsec away from the host halo. And in the bottom row, we can see that the old gas content has been removed from the dwarf during the close pericenter passage. And finally, this appeared like an isolated and red galaxy in the field. In general, our sample of splashback UDGs are located around of 2 times virial radius of nearest halo. And in the bottom panel, we highlighted the location of one of rated isolated UDGs. So also, we find an extreme example of splashback red UDGs that was preprocessed in a group and quenched previously to infold in this major halo, and finally was ejected about of 3.5 megaparsec away of the host halo. This will be in good agreement to explain cases like this quenched isolated UDG is 82 DG1 from Roman work located nearby of a void. Another of the point to consider is the difference of masses between red and blue UDGs in our sample at redshift 0. We believe that this mass segregation is due to remove the gas content and premature cut-off in the star formation, while the blue UDGs form stars all the time. Okay, like a bonus track, we talk about a possible origin of UDGs in TNG simulations. This because the splashback orbits only change the environment of UDGs, but not their structures. Previously to the interaction, these galaxies were UDGs, and the question is, how do UDGs form in TNG 50 simulation? We believe that this formation is mainly related to the dynamics of the dark matter halos. One way to quantify this is through the dimensionless parameter of spin. We use the definition of Bullock to measure this value. We observe in this plot the halo spin parameter with stellar mass relation. And we observe that for star forming UDGs present high values of spin respect to the normal dwarf in the field, with a typically value reported in the bibliography. And in the case of quenched UDGs, these present a lower values of spin halos. This due to the interaction with massive halos in the past. But when we measure these values of spin before the infall, we find that these values of spin are very high. That is, the halos have lost angular momentum. This is in good agreement with the work of Amorisco and Loew, where they describe that UDGs are an extension of dwarf galaxies with high spin halos. So, with a summary, we identified a sample of quenched UDGs in the field using data from TNG simulations. This population is different from the majority of UDGs in the field, which is star forming in good agreement with observational data. The quiescent UDGs in low-density environments are preferentially observed near to the past host and average distance to 2 times viral radius from this. They all had a passage in the past within a massive halo, and in the mass range 12.5 to 14 viral masses in log scales. Finally, when we trace the orbits back in time, and we can see that there is a close relationship between the time of closest approach and the time where the galaxies lost most of the gas content and after a quenching. This interaction, however, didn't change their size. The UDGs were UDGs previously of this interaction. We believe that UDGs in TNG simulations seem to form in high spin halos. some reference, and thank you.